Thanks for the introduction and thanks everyone for coming. Let me. Okay, so currently, if we look at current intelligent AI models, like let's say a foundation model in robotics, you can kind of give them some instructions such as pick up the banana, put it in a bowl, or move the banana to the bowl, even if you exchange the bowl. But at the current moment, these models aren't as general as you would hope for. In the sense that a lot of times to get the model to be able to do something like this, we've gotten over 10,000 or 20,000 demonstrations on this tabletop with all various combinations of objects. So what we really want is we want to build a general purpose intelligent robot in the physical world. And we want systems that can really robustly generalize to all types of different tables that we have, tables or settings or houses that we've never seen before, all types of new tasks, all types of other agents and environments. And I think the really challenging problem is that if we take a look at things such as natural language, although the models are not perfect on language either, but they at least are you're able to deploy these models on a wide variety of language tasks. But if you look at things such as embodied data, really we only have a very narrow amount of data because in the end of the day, we can only show a robot in a couple of different houses, and we can only gather so much data, but we can't really gather data for how a robot should behave in every single house in the world. So the question is, how can we build systems that can operate in the really wide distribution of settings that you would want in a embodied agent, given a limited amount of data? And a lot of the focus of my research and in this talk is this idea that you can solve a lot of these problems by simply trying to build some type of model of the world. And once we have a model of the world, then we can formulate decision making as some type of planning or inference on top of this model. And I'll talk about a particular instantiation of a model that really allows us to build agents that can generalize to a wide variety of different scenarios. So the overall general approach I'll talk about in this talk is this idea of building some type of probabilistic generative model of the world, and where we can now use this model to predict and plan adaptively through search. So once we have new goals or constraints, we can run inference on this model to get to solve these new tasks. And the second point is that we really want to build these models in a compositional or structured way, so that even if we enter situations that we haven't seen before, the models are still able to operate effectively because they're built off these components that you have seen. So let me first briefly talk a bit more about this first part. So let's say we have a task, climb up the stairs, and we have this image observation. So normally a neural network will take in this image and output a single action trajectory. And this is really great when your training test distributions are exactly the same, but a lot of the time you will actually enter a new environment where this becomes invalid. Maybe now there's an obstacle in front of you and you can no longer move upward. So a lot of this can be solved by, instead of just learning an explicit policy, which directly predicts an action trajectory to execute, we instead encode preferences over this entire space of actions. So in some sense, we can learn a model of of what good actions are in this environment by simply having a model that takes in an observation as well as action trajectory, and it simply just estimates the energy or utility for this action. So that when the action is good, the energy is low, and when the action is bad, the energy is high. And this essentially corresponds to learning a probabilistic generative model over the space of action trajectories. And now when you want to make decisions, now you have the search for inference procedure where you try to find the action trajectory such that the energy predicted by the neural network is low for this task. So why is this beneficial? So now we can combine this with some type of planning. So once we have this first energy function for climbing up the stairs over different action trajectories, now I can just simply add another constraint, such as maybe I want to ensure that the robot is safe, or I want to ensure that it is optimizing the objective function I care about. And now when I have these two functions, I can simply combine them together and optimize for actions that minimize both of these objectives. And now we can adapt and solve new tasks that we haven't explicitly trained our network on. And again, you kind of, to find valid actions, you just search for the prediction that minimizes the energy. Okay, so that's the first idea of how you can really, you can construct a generative model, where in this case, we're using this energy formulation, which I'll use throughout the rest of the talk. But this is a particular instantiation of how you can use a model to adapt to new tasks. So the second point is that you can really build these models in a somewhat compositional manner. So if we take a look at this distribution here, so in practice, a lot of times if we're modeling, let's say, the physical world, whether like how I'm talking right now really doesn't influence what the weather is like or how the rules of physics work. So the world you can kind of represent in a very independent manner. So if you want to represent a distribution P of x, you can often assume that really this distribution P of x can be written as a product of a bunch of subfactors. So we can have distributions that model different independent components of your system. And now we can represent or at least approximate the entire real-world distribution as a product of these independent factors. And the benefit of doing this is now if you can represent your distribution as a product of independent factors, now you can have your system generalized to areas of the distribution you don't have data for, because now each of these factors are locally in distribution. And in practice, a lot of the structures in the physical world end up being naturally independent, so that these independent structures can allow your model to operate in areas you don't necessarily have data for. And of course, it will be biased though, so sometimes your models will not be perfect, and you could imagine learning additional models to capture the issues with correlations. So that was just a general outline of how we can really use word models to get intelligent agents. Now let me go a bit more into the details. So first, I'll talk a bit more about this energy-based perspective and how you can learn these energy functions. Then I'll talk about how this really allows us to do planning. And finally, I'll talk about how this enables us to do some reasoning. So first, let me talk about energy-based models. So loosely, an energy-based model is a way to look at generative models where each generative model takes in input. So let's say I have an energy function for red trucks, so that when I give an image of a green truck, it assigns it high energy. And when I give it an image of a red truck, it assigns it low energy. And essentially, this energy function parameterizes this entire landscape across the space of images, so that all images of red trucks have low energy and all other images have high energy. And this energy function can be used to represent a probability distribution through the Boltzmann distribution. And one way to think about this is you can also view the energy function as some type of verifier over the space of generations, so that all generations that are good are assigned low energy, and otherwise all other inputs are assigned high energy. And to train these, and once you have this energy function to generate from it, you can use some type of Langevin dynamics. So you can use the gradient of the energy function. So your goal to generate a sample is to find a sample with low energy. And you can essentially use a noisy optimization procedure where you start with a random guess, and then you follow the gradient of the energy to find a sample that minimizes final energy. And to train these models, typically use some type of contrastive loss, where you have some ground truth data. You try to contrastly decrease the energy of this ground truth data, and you draw some samples from this energy function using the procedure I talked about earlier, and you contrastively try to increase the the energy of those samples. And in early 2019, we illustrated some techniques to scale these energy-based models to modern generative tasks. But loosely, it looks something like this. So initially, let's say I want to construct an energy function for red trucks. Our energy function at the beginning is just flat. So both red trucks and Gaussian noise get assigned the same energy. And then you just pull down the energy of red trucks while pulling up the energy of this Gaussian noise. And now you have a slightly more refined energy function, so that when you sample from it, you get an image that looks a bit more like a red truck, and you just pull up the energy of the red truck and decrease, or the noisy red truck and decrease energy of ground truth red trucks. And you repeat this until all your energy minima are red trucks, at which point you're decreasing the energy of red trucks and increasing the energy of red trucks, at which point training cancels out and you have the distribution corresponding to red trucks. And you can also interpret diffusion models as a type of energy-based model. So this was the generation procedure we proposed in early 2019, late 2018. So you have with this Gaussian noise and running some Langevin dynamics, you eventually get these images. The diffusion procedure ends up being very similar, and you can just interpret the denoising network as predicting the gradient of the energy function. And the nice thing about this is I'll talk a lot about combining these energy functions together. And you can do a very similar thing with diffusion models. So let me talk a bit about actually the operation of combining energy function. So first, let's say I have a red truck energy function and I sample or optimize from it. Then I'll get an image of a red truck. The nice thing is now at test time, I can take a red truck energy function and I can define another energy function, like energy function for deserts. And now by just directly optimizing both of these, now I get an image of a red truck in a desert. So what the nice thing about this energy formulation is now I can combine multiple factors together, or constraints together, to get a sample that satisfies all these constraints. And so in general, there are you can by combining these energy functions, you can manipulate different probability distributions. So if I have an energy-based model for a distribution P1 of x and a separate one for a distribution P2 of x, then I can draw samples from the product of the distributions P1 times P2 of x. With a different set of operations on combining the energy functions, I can also draw samples from the mixture distribution P1x plus P2x. And I can also draw samples from the distribution P1x divided by P2x by subtracting two energy functions. So this allows you to, so one nice thing this allows you to do is now you can use these operations to generate more complex samples. So let's say I have a really simple text-to-image model. So I have a model that takes in text descriptions such as a horse and gives me a likelihood distribution over all possible horses. Now, by simply manipulating the probability distributions defined by each of these generative models, I can generate a scene of a horse where it's on either a sandy beach or grassy plains where it's not sunny, which corresponds to some distribution that looks like the one in the bottom. And what you can get is you can correspondingly get these images where initially you have a horse, and then as you combine these distributions together, eventually you can get an image on the right of a horse where it's either in a sandy beach or grassy plains where it's not sunny. And one nice thing you can do is by combining these energy functions is that you can also use this composition as a way to really understand scenes. So now let's say I have an image where here I have three objects. What I can do is instead of trying to generate a sample by composing these energy functions, I can instead say, given this sample here, what are the energy functions I should compose to best describe this image? So now given this image on the top here with three objects, I simply try to infer the parameters, the three latents conditioned on each energy function so that the energy minima corresponds to the ground truth image. And when you do this type of procedure, what you find is that you can give these inputs of images where here we have 3 or 4 objects, and then our approach, which is the one on the rightmost column, you can actually infer 3 separate energy functions that describe this input, which corresponds to the position of the 3 objects on the top, or corresponds to the positions of the 4 objects or 5 objects on the bottom. And the nice thing about this procedure where we're able to describe an image by simply inferring the set of energy functions that describe it is that it allows us to generalize to much more complex scenes. So here at test time, we're just giving scenes consisting of up to 8 objects. And now by simply trying to find the composition of these energy functions that best describes this image, we can now infer the positions of all 8 objects, shown in the bottom right. And also, this type of procedure where you're trying to explain these images generatively also generalizes pretty well to objects and new textures. So it's by simply training these functions on images shown in the previous slide, we can also generalize to these images with much more textures. And you can also use this to infer the number of objects in the scene. So you can simply try to, let's say I have a scene with an unknown number of objects. I can try to explain the scene using composition of 3 functions, composition of 4 or 5, and see which one assigns us the minimal energy. And what we find is that if you do this, then the number of composed energy functions that gave you minimal energy to the sample corresponds to finding the object with the fewest number of corresponds to finding the ground truth number of objects in the scene. So in a sense, that was a brief introduction on energy-based models, and I briefly illustrated how this idea of compositionality can allow you to generate scenes that are more complicated, as well as understand scenes that are more complicated than the ones you've seen before. So now I'll talk a bit more about how we can use this idea of compositionality and energy-based modeling towards this domain of planning. So in planning or decision making, what we typically want is we have some type of test time objective. So either we want to optimize a reward function, we want to reach a goal, we want to optimize a value function, and really we want to recover the sequence of trajectories that get us towards this goal or specification. And we can formulate this as an energy optimization problem where on the top, we learn an energy function that assigns low energy to all feasible trajectories in this environment. And we can simply formulate the objective we want to optimize as a cost function or a second energy function over the trajectory. And now making decisions in this environment corresponds to optimizing the sum of both of these two objectives. So you want to find a trajectory that is low energy under the first energy function, so it satisfies feasible dynamics, while also reaching the goals or values that you wish to optimize. So as an example of what you can do with this procedure, let's say I have an energy function for trajectories. where this just assigns low energy to all the space of all possible trajectories in this environment. I can simply hand define a second energy function that specifies which assigns infinite energy if the start state and goal state are not the ones I specified, and otherwise assigns low energy. So now if I combine these two energy functions together, I have a new optimization problem where where solutions that satisfy the sum of these two energy functions correspond to plans from the start state to goal state. So this allows us to use composition to construct a zero-shot goal-seeking policy. So here we train models on, so we just trained the first energy function on random trajectories in this maze, and now we specify the start state and goal state. And by optimizing, this procedure is able to eventually find these trajectories of up to length 512 that go from the start state to goal state. And you can compare it with some baselines, and you find that since this is a pretty long horizon decision-making problem, there's very sparse rewards. So if you try to use some type of offline reinforcement learning technique, they perform much worse. And also our approach is applicable across different types of start and goal states because we're simply combining models, while all these other methods require per task specific training. So another thing you can do is you can simply just take this energy function for trajectories, and you can just combine it with a separate energy function that just specifies your value function or reward. So you can either train a separate network to regress the reward at each state, or a model that can regress the value of a state. And now by combining these models, now you can construct a policy for optimizing our RL objective. And what we find is when we do this type of composition, we actually are able to perform very similarly to the state-of-the-art offline reinforcement learning techniques. But the thing is, we actually don't have any explicit training. We simply just compose it with some type of reward function. And you can combine these models not just at you can combine these models not simply at the full trajectory level. So you don't have to just combine a trajectory level model with a goal function. You can also combine different chunks of trajectories together. So here we have this pretty complicated maze where we want to go from one start location to another. And what we can do is we can effectively just combine energy functions defined over chunks of the trajectory. So we have one energy function defined over the yellow trunk, one over the gray one, the purple one, the brown one. And then you can jointly optimize all of these chunks in parallel so that you can go from your start state in yellow to your goal state in blue. And here, so as an example of this in practice, so let's assume we have some offline data set like this, where each trajectory you see is just the particle, the ant loosely moving locally around itself. And what we can do is by combining many of these locally moving chunks together, so we can jointly optimize these chunk models, we can now get a consistent plan that goes from the start state to goal state. So we can kind of stitch together these energy functions defined over local chunks and compose them together to get a generative model that goes from your start state to goal state. And you can also use this to, you can also combine this with some type of foundation model. So let's say we have some type of large language model, a video model, an egocentric action model. We can do a similar thing of combining the information across all three of these models, where let's say we have a hypothetical task where we want to make a cup of tea. On one hand, if you use a language model, the language model can give you these pretty useful high-level information on the steps necessary to make tea. But it doesn't really tell you any detailed visual information. A video model tells you a lot of information about how to actually, the visual details of what it means to pour a cup of tea. An action model can tell you a lot of detailed control information on how you should manipulate objects to make this cup of tea. So you can imagine that in this setting, all three of these models have different sources of information, but you can use you can kind of use this similar energy optimization procedure to actually solve this problem, where you essentially want to get a text trajectory, an image trajectory, and an action trajectory that is consistent across all three of these models. And this corresponds to an energy minimization procedure, where we're trying to optimize for a trajectory of text, a trajectory of images, and a trajectory of actions are highly likely under each of these three models. So if we can find a trajectory that satisfies this constraint, then this means that since the text trajectory is high likelihood under the language model, it's a plausible goal given or a plausible set of sub-goals to solve a task. Since the image trajectory is in distribution under the video model, it's a plausible set of visual states that we can actually use to actually accomplish the goal, and similarly for the action trajectory. And in practice, to actually optimize this energy objective, you essentially do this bi-level sampling, where you sample different language generations. You compute the likelihood of the language generations under the video model. You choose the one that's the best. And similarly, you generate different video generations, and then you choose the one that maximizes likelihood under the action model, and you select the best one. And this bi-level optimization eventually allows you to get a sequence of language, images, and actions that maximizes the likelihood of all three of these models. So here's an illustration of this. So let's say I have a goal where I want to stack a red block on top of a cyan block and place a brown block to the right of the stack. So initially, the language model, since it can't see the scene, might say something like, place the cyan block in a brown box. And then you just simply pass it to the video model. It tries to generate a plan. You can also compute an elbow bit of the generation. And assigns very low likelihood to it because this is not plausible in this environment. And you just keep sampling from the language model until you get a plan that is consistent. So maybe it's place the white block in the cyan bowl. And this one now is actually plausible in the environment under the distribution learned by the video model. And now you can pick up the white block and place it in the blue bowl. And by repeating this at all three levels, you can eventually get a system that can solve this full long horizon task of stacking a red block on top of a brown block and placing a yellow block to the left of the stack. And you can, and I guess the energy functions you compose, they don't necessarily have to be likelihood. So you can also use other, like the models themselves can define these objectives that you want to optimize across these three plans. So one idea is that you can simply have a VLM as your energy function for assessing how good a video plan is. So here you can just ask the VLM, given a video plan, where my goal is put the fruits in the top drawer, and you can just have the VLM estimate how much progress you've made. So here, in this case, when the cabinet is not open, the VLM would estimate low progress. And on the other hand, if your goal is put the fruits in the top drawer, and if the video is something, or the image plan is something where you open the cabinet, then the VLM can estimate more progress. So if you formulate optimization in this way, where you have the vision language model define your optimization objective with a video model and action model, then you get some type of tree search, where essentially you're again trying to find the sequence of language plans and video plans, but now you're just recursively expanding it in a tree search. So given the start image, you generate different possible language plans, and now the video model renders each of them. But now the VLM actually selects the one that's the most promising, and you again repeat this over time to eventually get this overall plan of opening the top drawer, placing the banana in the top drawer, placing the apple, and then closing the drawer. And you can actually implement this in practice. So we just took a pre-trained VLM, a pre-trained video model, and a pre-trained action model. And this is a zero-shot task where you want to put the fruits in the top drawer. And you can see that the robot is able to open the cabinet, pick up one object, pick up the second object, and then eventually solve the task. And here's another example. So here we have a pretty long horizon goal of making a line out of these blocks. And we can do the same planning procedure, and then we can get this somewhat pretty detailed set of language instructions for solving this task. And you can also get this corresponding completely generated video plan. So this is a generated image plan for making a line. And you can see that you can actually manipulate all the objects very precisely to make an overall line. And you can also convert this to real robot execution. I don't know why it's not showing. Well, anyways, it turns out that it performs better than all the other approaches, but you can't actually see the bar plot. Last part. So the last thing I'll talk about is how you can actually use this procedure for reasoning. So finally, you can also formulate the problem reasoning. It's a type of energy optimization procedure where now in reasoning, let's say I have a problem. I can just formulate solving the problem is finding a solution that minimizes my overall energy function. So you can formulate getting a solution. The final prediction in your network is simply finding this. So given a problem, you can just formulate solving the problem is finding a solution that minimizes the overall predicted energy for that problem. And then you can use some type of, and essentially, if you try to do reasoning with this energy-based framework, then it's this search procedure. Well, now you have this inference time search procedure to really find the solution that has minimal energy. And what we find is that when you do this, you can formulate reasoning in this energy minimization procedure. And one nice thing about this is that you can actually just improve your performance as you run more steps of optimization. Because now your increased steps of computation is simply just running more steps of optimization on your energy function. So on the left, we have this energy optimization procedure where as you run more steps of optimization, the performance gets better. While if you use something like a recurrent neural network, the performance gets worse. And what we find is that this type of procedure where you actually use the energy function to define this verifier over the space of solutions and then use optimization to find the answer, it ends up allowing you to generalize a little bit better to more complicated scenes, as well as to harder problems. And that intuition is that if you learn an energy function, you're simply just learning to verify whether your solution is correct or not. Well, if you try to train a network that explicitly generates the answer, you actually have to do the entire computation to solve the task. So learning this energy function is a more decoupled way to learn your task, so that you have to learn less and it's more liable to generalize. And a nice thing also about learning these types of energy functions is that it allows you to do somewhat generalizable reasoning. So let's say we have a task where we want to color a bunch of nodes on a graph, where each edge specifies that two nodes must be different colors. Then what you can do is to solve this pretty complex reasoning task, you can actually decompose it into simpler problems where you can have an energy function define the coloring of two nodes. So each edge corresponds to the energy function. So solving the entire task corresponds to minimizing energy functions across all edges in this task in this graph. So this allows, and the nice thing about this formulation is now you can solve much more complex coloring problems than the ones you've seen before by simply combining more of these models. So what we find is, so let me give two examples of this. So on the left, we have an A queens-like problem, where here we just simply learn an energy function that assigns a queen on law in a row. While on the right, we simply learn two-node coloring model. So it just simply learns to make one node a different color than the other one. And what we find is that at evaluation time, if we, let's say we want to solve this 8 queens problem, where we basically want to put 8 queens on this chessboard so that none of them attack each other, we can simply solve this task by just combining energy functions across each diagonal, each row, and each column. And by composing and optimizing all of them, we end up getting a solution for the entire 8 queens problem. And what we find is that just by doing the zero-shot composition, you can actually solve tasks with over 97% accuracy. In the 8 queens problem, and you have similar numbers with this type of graph coloring problem. And you can also do this for 3SAT. So on 3SAT, we trained a model on SAT problems with 20 variables and 91 clauses. And what we find is that by simply composing many of these energy functions over each 3SAT clause, so we simply learn an energy function per clause, now we can generalize and solve much harder variants of SAT problems with 50 variables and 218 clauses. And the interesting thing is all these baselines we compared to are different learning-based combinatorial optimization techniques, or specifically methods optimized for SAT solving. So it's surprising that this type of energy composition can actually solve quite a few interesting and complicated tasks. And then, let me move to this side. And a final thing you can also do is you can also apply this type of energy minimization framework to language models. So you can simply have a language model serve as your verifier, where you can just ask the language model, is this answer correct or not? And you can construct multiple different verifiers by just asking the model to verify different parts of your solution. So here's an example of this. So let's say I have a simple problem where I have a simple math problem where I want to convert this number to improper fraction. And what I can do is I can just simply prompt language models to verify these solutions in different ways. So each of these language models are now like these energy functions, and then you can ask one to just directly check if the answer is correct or not. You can ask another one to check if the unit conversions are correct, and so forth on different aspects. And what we find is by having these language models per aspect, and now you can get a score for this input by simply computing the judgments from the language models of true or false for each aspect and summing them together. And now to get an overall final correct answer, you just simply generate many solutions and select the one that has the minimal totals or the highest number of approvals. And what we find is interestingly in this setting, by having more and more of these verifiers or more of these models that just assess each whether a solution is correct or not, we find that the performance seems to monotonically mostly increase. I mean, there are a couple of plots where it seems to decrease, but most of the time, as you increase the number of verifiers, the performance increases. And you can also compare this to other approaches to do test time scaling in language models. And we find that just by composing more verifiers and then optimizing these verifiers, we're able to get much better performance with more outputs compared to other previous approaches. Great. So overall, I guess I introduced a type of world model which is based off this energy-based formulation, and I talked a bit about how you can use composition on top of these models as well as search on top of the models to solve a wide variety of problems towards the task of constructing intelligent robots. Thanks everyone for listening, and happy to take any questions.
And then the two after going through and then.
Good talk. So when you talk about composing independent factors of an energy function, I think most of them applies to the cases where multiple objectives have to be pursued in parallel. But then for an agent in an open-ended environment, sometimes multiple goals should be pursued in a sequence instead of pursuing in parallel. So I think that is partially responded by your later work of stitching multiple trajectories in chunks. Then I think the follow-up question is, how do you decide the boundaries of chunks?
Yeah, so I guess you could imagine that you can do some type of refinement. So what you can do is you can assume some rough chunks, and then as you're running this optimization procedure, you can just you can expand the chunks or decrease the chunks during the you can also try exploring. So you would just assume some rough chunks at the beginning, and then you would maybe refine them over the course of optimization.
Okay, that makes sense. Thank you.
Thanks.
Hi, Yilun. Beautiful talk. Yeah. So the question is a little bit general, but I'm not sure there's a general answer. So you mentioned this connections between diffusion models and energy-based models, and diffusion is kind of learning the gradient, and energy is learning the scalar functions. And I think I can see pros and cons for both approaches. If you learn the gradient, the neural network may not return you a gradient, and if you learn the energy, and the gradient may not look good. So is there a general kind of strategy of what should your neural network learn, the scalar or the gradient?
Yeah, so I think when you learn the scalar, the nice thing about learning the scalar is you actually know how well you're optimizing, so you actually have a value for your optimization, while if you're learning the gradient, you have no idea how well you're optimizing. I think that learning the energy is a bit harder, it's a bit more expensive than learning the gradient, because now you have to compute the energy and then take the gradient of the energy to actually compute the gradient. So I think in terms of expressiveness, learning the energy function, it gives you more tools for effectively optimizing the models and for composing models, but learning the gradient is a little more efficient in terms of if you know that all you want to do is just add a couple energy functions together, then directly learning the gradient can be a little more efficient.
Thank you so much. Great answer.
It's working. Yeah. Thank you for the talk. I really liked it. My question is more of just a nitpicking type of clarification question. One of the nice results you showed in the reasoning part is that when you iterate over the increase the iteration step in the RNN, it actually gets worse, right? I was already wondering about the result because RNN, if they converge to a fixed point, then they are also kind of minimizing some type of energy function they are trained on, right? So I was wondering why that result happened, why does the RNN, if they approach to the fixed point and minimizing some type of energy function that they define by themselves, why does it actually getting worse over time?
Yeah, so I think at least the evaluations we were doing, what we found is that as we ran more and more steps in RNN, it seemed like the activations actually kind of exploded. So I guess either it converges or so I guess it depends on whether the latent space converges. Sometimes it converges, sometimes it starts exploding. So I guess what we found on our settings was it seemed to explode. I suspect that that probably was more tuning. You could probably get it to at least converge. But at least from our simple implementations, it seemed like the activations were actually exploding over time.
I see. Very sorry. Just one small following question. So is it just a simple vanilla L-man RNN?
I think it was an LSTM.
Oh, I see.
So it shouldn't really explode, but that's what it seemed like what was happening.
Gotcha. Thank you.
Thanks for the great talk. So maybe bring it more towards neuroscience. This seems like a way of generalizing sort of speech behavior, which we often characterize like human intelligence as. Do you have any thoughts on like what a neural implementation of sampling from these probability distributions could look like?
Yeah, so I guess I don't have too much background in the neural area, but this would be an area I would be very interested in exploring more. Yeah, thanks.
Hi, real. Have you tried applying some of your approaches to like adversarial robustness of language models, especially for like AI safety related things, and seeing if your approaches can like target some of the existing models in a way that it adversarially breaks them, and then maybe generating insights into making them safer?
Yeah, I think so. I think some type of this energy-based training objective function could be one way to make language models more robust. In the sense that we have this contrasted procedure where we try to generate these incorrectly low energy samples from the energy function, and we try to increase the energy of those samples. So you could imagine that maybe some adversarial issues with language models, if you have more of this contrasted procedure, then maybe the language model will be better shaped and won't have as many vulnerabilities.
The addition of different energy functions corresponds to the product of their probabilities. And sometimes that's going to be fine and sometimes it might not. So like a blue banana would be just fine if you multiply the color energy function, add the color energy function to the shape. But other times it might not work out well. Like you might have independent features like eyes and mouths, and you don't want to put them anywhere. You want them actually organized. So when is this kind of composition going to work well and give you something that's nicely in distribution versus out?
Yeah, so yeah, it's definitely the case that we're assuming some type of independence, and yeah, in a lot of cases you might not want this independence, or like so what we find is because so one nice thing about these current generative models is you're effectively learning like let's say we're learning the distribution of eyes and mouth. Well, we're actually learning the first model is actually learning the distribution of eyes plus human faces because it only sees human faces, and the second model is also learning mouth plus human faces. So in a sense, when you compose these two models together, you actually do get a reasonable face because there's an implicit constraint that you must generate a feasible sample that you've seen before. So I think the fact that you have the additional constraint that all these models learn what a feasible sample is, that solves a lot of these issues of independence. But yeah, in general, what we find is that when you let's say you want to generate a dog and sky where these are just incoherent concepts, then we find that the model just generates something that like kind of looks like an optical illusion, but isn't actually one thing or the other. So I think that this type of system doesn't work that well when you want to generate samples that are very, very different than what you've seen in your training data, because now like you don't have this regularizer that these samples must be similar to the data you've seen before.
Thank you.
Yeah.
Very interesting talk. I had a quick question about the part where you showed reasoning being done by these energy-based models. So for the example of 8 queens, for example, how do you get rid of the problem of backtracking in these kind of problems? Is it just outsourced to the optimization process? And if so, how does all of this scale?
Yeah, so I didn't talk at all about the actual optimization procedure for this. So yeah, for the 8 queens problem, we actually have some type of, so we actually do around 1,000 parallel beams at once, and we actually do some type of resampling, and we add some noise, and we have some recent work also on backtracking through this optimization procedure. So all of these do help a lot, and yeah, it's definitely the case that as you compose more of these functions together, the optimization problem becomes much harder. So I didn't have time in this talk to talk about the techniques to solve those, but you do need to have some smarter optimization algorithms as you compose more models together.